So you already know what is a relation, right? So you have done this, right? During your 12 relation part, you have done this, right? Or it is a new for you? Yes. Is this new for you or you already know? Yeah, say something. Both cannot be true, right? Both are contradicting each other. So one of them will be true. So is it new or you already know some of the part of relation, maybe equivalence relation up to? You know that, right? If people are not listening, yes.
Yes.
So you already know this. And what about the set? So actually I want to know regarding that countability. Do you know that countable set, uncountable set, all of this concept?
Not sure. We just
Yes.
I don't
Huh.
think we've been formally taught.
Okay, okay. And what about that cardinality? Cardinality of a set, that is that there are many kind of cardinality, right? So many types of infinity. So you don't know that. So you only know that little bit of relation, right? That up to equivalence relation. Do you know poset?
Mm,
Yes, what?
no, sir, I don't think so.
Okay, okay, okay. Fine, fine, fine. I'm just asking because I should have rough idea. Okay, so anyway, but I will not skip anything because this is a course and I have to do whatever you have in your syllabus. So I am forced to do that. So I will start with the relation. Okay, I should share my screen. Okay, so can you see that white screen?
Yes, sir.
Yes, sir.
Okay, so I start with relation. Probably today's class you more or less know most of the thing, but from the next class I think there will be something you do not know that. So even if you are listening my recording after the lecture and if you are not attending the live lectures, then I suggest you should attend from the next lecture, because from the next lecture we will do something which will be done in the class, but probably you do not know that. Okay, so this is our lecture 6 and this is on relation. So I start with the definition of relation. So if you feel that I am going very slow, then you should tell me because I do not know about my speed. So if you feel it is fast, I think it is not fast. But if you feel that it is fast, then you can tell me that so that I can go slow. And if you feel that it is slow or very slow, then you also suggest that because we also take your suggestion and improve ourselves. Okay. So if you feel that this is slow, then you should tell me. Then I can go little bit faster than before. So let A and B be two sets. Okay. Now a binary relation from A to B is, what is that a relation? It is just a subset of A product B. Is a subset of just A Cartesian product of B. Think I got a question or what? Nothing. Okay. So what is a relation? Relation is just a subset of A cross B, right? Now let R such a relation which is subset of A Cartesian product of B be a relation. So that's mean it is a collection of some order pair, right? Now if the order pair AB belongs to R, right? Then we say that A is related to B. Okay, and we generally write it is, so we denote this by, we also write in this way A R B. So it's mean A is related to B, and this that's mean A related to B, and that AB, that order pair AB belongs to R, both are equivalent. So why we are saying that it is order pair? So that's mean AB, the pair AB and the pair BA, they are not same. Okay, so that is the reason we are calling it is an order pair. Okay, now if this order pair AB is not in R, then we say that A is not related to B. Related to B. And also this is can be written as A, it is not related to B. You just write first A, R, B, and then just cross it. Okay, fine. Now this is a relation actually. So this definition is very simple. Now we can look at one example. So let A equal to say 0, 1, 2 and B equal to AB. Okay. And say R equal to this collection 0A, 0B, 1A, 1B. So then we generally say here, note that R is a subset of A cross B. So this is a relation, no doubt. And also we can write that 0 is related to A and 2 is not related to A. Okay, fine. So in general, during this course, so any relation from A set A to B is not a very interesting. So we generally focus on, or maybe we are interested on relation from a set A to itself. Okay, so we are actually interested on this. So generally we define everything from a relation from a set A to a set B, but when we do all the calculation and many important theorems, most of the cases we will assume that A and B both are same. That's mean the relation is from a set to itself. So we can write it is as a definition. So a relation, in that case we say that in a relation on a set, on a set A. Okay, we will not say that from A to A, we will say that on a set A means it is a relation from A to itself or from A to A. Okay. And also when we define, we know that R is a subset of A cross B or here A cross A, but generally we do not write in this way. We generally write R in some of, you can say some of the term in terms of language. For an example, so you will see that one only. So example, we can take A equal to the set 1, 2, 3, 4. Okay. And we define R. Should define R on A such that A or B if and only if A divides B. So in this way. Okay. So that's mean here what is R? So we can ask that then in that case, what is R? Now it is easy to find that. What is R in that case? So R is the order pair. We know that 1 divides 1. We know that 2 divides 2. So first of all, we know that 1 divides 2, 1 divides 3, 1 divides 4. So we have this. Then 2 divides 2, 2 divides 4, and 3 divides 3, 4 divides 4. So this is our R in that case. Okay. Now there is a simple. So if I ask you that how many relations are there on a set with n elements? So how many possible relations? We can say that possible relations are there on a set A with n elements. Okay, so this answer is very simple. Now A has n elements, that imply A cross A has n square elements, and we know that the collection of all possible subsets of A cross A has total number of subsets the collection of subsets. Okay, not collection of subsets, it will be a subset. We are not taking that element. Subsets of A cross A is 2 to the power n square. So therefore we have, so thus we have 2 to the power n square relations or possible relations. Right? So this is very easy to calculate. Fine. Now we define some important concept. You already know that. So first one is reflexive. Okay. So a relation R on a set A is said to be reflexive if all the order pair, this A cross A belongs to R. For all A belongs to A. Okay, so this is called reflexive. And similarly, we can define symmetric. Symmetric means, so whenever the order pair AB belongs to R, that will imply BA belongs to R. Okay, or better to write in that way that R is said to be symmetric. Symmetric. If this happens, that's mean, so whenever A B belongs to R, that will imply B A belongs to R. Then we say that R is symmetric. In similar notion, we can define antisymmetric. So again, so R is said to be antisymmetric if your if you have AB belongs to R and BA belongs to R, that will imply A equal to B. So this is called antisymmetric. That's mean if AB belongs to R, that's mean if A related to B and also B is related to A, both will imply A equal to B. If this happens, then we will call the relation R is antisymmetric. And there is another important concept, it is called transitive. So transitive means again R is said to be transitive if A related to B and B related to C imply A C is related to R. Means A and C are A related to C. That's when AC belongs to R. And it should be true for all A, B, C in A. Here we should write here also for all A, B belongs to A. For all A, B belongs to A. Okay. So we can see one example. Is there any question? No, it is fine. So how many students are there? Oh, 96. It is dropping. Fine. Now we will see one example. Now show that the relation R defined on Z, which is defined by, it is A related to B if and only if 3A plus 4B is divisible by 7. Okay, for AB belongs to Z. Okay, so we are taking our set is Z. So that's mean R is a relation on Z. Okay, and it is defined this way, that A is related to B if and only if 3A plus 4B is divisible by 7. Okay. Now discuss what about R. So what are the properties of R? The properties of R. So that's mean, is it reflexive or symmetric or transitive? What? Now you can also try this. This is very simple one. So first of all, you can check that it is easy to see that it is reflexive, right? Because if you choose any A belongs to Z, or you can start with reflexive. We'll just check it is reflexive or not. Okay. So take A belongs to Z, then you can check that 3A plus that is 4A, that is 7A, and is divisible by 7. Right? So therefore A is related to A. Or you can say that AA belongs to R, or A belongs to Z. Right? So therefore R is reflexive. Right? So this is done. This is very simple. Now we can check it is symmetric or not. Symmetric or not. Okay. Now we check, we take A, B belongs to Z, any arbitrary, such that A is related to B. Okay. So that's mean 3A plus 4B is divisible by 7, right? Now then we need to check that it is symmetric or not. That's mean 3B plus 4A, that is divisible by 7 or not. Now 3B plus 4A, this you can write as 7 of A plus B minus, that is 3A plus 4B. Okay. Now this is divisible by 7. This is divisible by 7. So therefore whole of this is divisible by 7. So therefore B is also related to A, right? So thus A related to B will imply B related to A for all A, B belongs to Z. Okay, fine. Now we can check that transitive. Okay. Now we take A related to B and B related to C. So that's mean 3A plus 4B and 3B plus 4C are divisible by 7, right? Now we need to check that A related to C or not. Now if we take A 3A plus 4C, now this can be written as 3A plus 4B plus 3B plus 4C, now minus 7B. Now this is divisible by 7, this is divisible by 7, this is divisible by 7. So therefore whole of this is divisible by 7. So therefore A related to B and B related to C imply A related to C. Okay, so therefore thus R is reflexive, symmetric, and transitive. Okay. So what about antisymmetric? R is antisymmetric or not? Yes. Can you quickly tell me that R is antisymmetric or not? So R is not antisymmetric. Why? Because A, you can see the 0 related to 7 and 7 related to 0. But we know that 0 is not equal to 7. Right? So it is not antisymmetric. Well, so we have three important concepts: reflexive, symmetric, and transitive. Now we define the concept of equivalence relation. Equivalence relation. Now what is that? Now a binary relation on a set X is said to be an equivalence relation if it is reflexive, symmetric, and transitive. Okay, so if you have a relation which satisfies these three properties, that's mean reflexive, symmetric, and transitive, then we will call that relation as an equivalence relation. For an example, the previous one. Oops. Example. The previous example of R is an equivalence relation. Okay. Now, obviously, so now this actually defines another term called equivalence class. Equivalence class. So now let R be an equivalence relation on a set X. Now then the equivalence class of an element A under the relation R is defined by, so we write it is as a class of A. Okay, so you can write in this way as well, that class of A, and that is defined by all the X from the set X such that X is related to A. Okay, you can say that A is related to X as well, because we are talking about the equivalence relation, right? So here X are A and A are X, both are actually same, right? Both are same in the sense that if X is related to A, then A is also related to X because it is symmetric. Fine. So that's mean we can see one example. So in the previous example, so X was our Z and R was, that's mean A, R, B, if and only if 3A plus 4B is divisible by 7. This one. So we have shown that. So R is an equivalence relation, right? So therefore, it should have some equivalence classes as well. Now here, R is an equivalence relation. So therefore, we can talk about the equivalence classes. So here, class of 0 was just 0 plus minus 7 plus minus 14 in this way. Now, can you quickly tell me what is class of 1? Yes, what is class of 1? Now tell me that. Yes. So what is class of 1? If people are not listening,
For one, it is 1 comma.
Plus minus 8.
So for one, it's 1 comma 8 and so
no,
on, and on the
right,
negative side, it's minus 6 and
right. So it is actually this one. You can verify that. Oh, sorry. 1 plus minus 21, etc. Good. Right, so in this way we can define the classes. So there is a tutorial problem on these classes. You can solve that. So that is very interesting. So you can see that actually that class of this 0, 1, 2, you can see that they are either equal or disjoint. And also you can see that you know that what is a partition of a set, right? So I did not define that. But if you know that partition of a set, then you can see that Z has a partition of this. That's mean class of 0, class of 1, class of 2, up to class of 6, you can make a partition of Z. So that's mean Z can be written as a disjoint union of those 7 classes. Okay, so there are some tutorial problems on that. So you can try that. That is very interesting. Fine. So now we have defined relation, equivalence relations. Now we can, if we have two relations, then we can make the composition as well. So composition of relations. So let R be a relation from A to B and say S be a relation from B to C. So that's when you have a set A, you have a set B, you have a set C. So this is your R and this is your S. Okay. Now then you can define a composite relation S composition R from A to C. Okay. Then the composite relation S compose R from A to C is defined by, or you can say that this consisting all the order pair AC where A belongs to A and C belongs to C such that, or we can say that for which there exists B belongs to the set B such that AB belongs to R and AC belongs to S. Oh, BC belongs to S. Okay, so that's mean how to find a composition relation S compose R. So if you have a relation R from A to B and if you have a relation S from B to C, then you first choose any pair. You shall first choose any pair and then verify that there exists a B such that AB belongs to R and BC belongs to S. This happens or not. If this happens, then we choose that pair AC and we say that AC belongs to the composition S compose R. Okay. And if there is no such B, then we will not take AC in that relation S compose R. So that's all. This is very simple. Now again, as I told you that, so we are always interested on the relations on a set, not from the different set from A to B, right? We generally interested on a set because then only we can define that reflexive, symmetric, transitive, antisymmetric, all of this stuff. So that is the reason when we define something, we define in general from A to B, but when for our purpose, we generally take A and B both are same. That's mean a relation on a set instead of from a set to another. So similarly, we can define okay, first of all, we should say that for a relation R on a set X, we can define Rn for n equal to 1, 2 in this way. Are defined recursively by R1 equal to R and Rn plus 1 equal to say Rn composite R. Okay, so in this way we can define actually R power n. And why we are defining that? So you will see why this is useful. So first of all, to understand this concept, we can take one example. Now, whenever we are saying we do some example, you have to work out that. Okay, you should say something because otherwise I feel like that I am talking with the computer only. There is no one behind that. And also I know that not every students are listening. So here maybe 90 students are there and there are few students who just log in and just go out somewhere. And maybe they will come back at maybe 11 and then they will just stop the meeting. So I know there are some students there. But I hope that those type of students are very less and most of the students are listening. So I assuming that, okay. So you should say, okay, so whenever you are doing some example, then you should participate on that. So we take A equal to 1, 2, 3, 4 and R equal to say 1, 1, 2, 1, 3, 2, 4, 3. So these 4 only, okay. So then find Rn. Now, first of all, it is you can just verify this by your only by using some mouth calculation, right? You don't have to write anything. So what is R square then? Can you just quickly tell me?
1 1,
1 1,
2 1,
good, 2 1,
3 1.
3 1,
3 1,
4 2.
4 2.
4 2. So these are all good. Now what about R3?
1 1, 2 1, 3 1, 4 1.
Right. 4 1. This. Now you can check that since everything is 1 1, 2 1, 3 1, 4 1. Now if you compose with that, right, then you will always get 1 comma 1. Right? So sorry, you will always have to take with this one only. So you will get the same object. So therefore we can say that this is actually Rn for n bigger equal to 3. Right? Now why this is very useful? So now we have a theorem. The relation R on a set A is transitive if and only if R power n subset of R for n equal to 1, 2, 3, etc. Now this portion is very simple. That proof is not very difficult actually. So first we do that if part. So that's mean if Rn subset of R for all n, then R is transitive. Now this is very simple proof. So assume that Rn subset of R. So in particular, R square is subset of R. Okay, fine. Now we have to show that it is transitive. Now assume A related to B and B related to C, right? Now then your A, you can see just take the definition. Since we have already A, B, such a B such that A is actually related to B by the relation R square. Oh, sorry, A related to C by the relation R square, right? By the definition. Now that will imply actually that AC belongs to R square and that is subset of R. So that's mean AC belongs to R, that is A related to C. So thus R is transitive. Okay, so we have taken A related to B and B related to C and we got A related to C. So therefore R is transitive. Now we do the only if part, that is that implies. Now assume that R is transitive. Now since we have to prove that Rn subset of R for all n So we use the principle of mathematical induction. Okay. So by principle of mathematical induction. So we have the basic step. We can verify what is our basic step. So take n equal to 1. So for n equal to 1, the statement Rn this is trivially true. Right? Now we go to the inductive step. Inductive step. Okay. So let Rn subset of R for n equal to k. Okay. So for some k bigger equal to 1. Okay. Now we need to show that Ark plus 1 subset of R. Okay. So that is, we assume that Rk subset of R. Okay. Now let AC belongs to Rk plus 1, which is by the definition Rk compose R. Right? Now since this belongs to this, so by the definition, so there exists X belongs to A such that, what was our set? Okay, our set was A. So there exists X belongs to A such that AX belongs to Rk and XC belongs to R. But we already know that Rk is subset of R. So therefore this is subset of R. So then we can say that AX belongs to R and XC belongs to R. Now since R is transitive, we can say that AC belongs to R. That's when A is related to R. Now we have assumed that AC this order pair from Rk plus 1 and we got this is belongs to R. So therefore we say that Rk plus 1 subset of R. Okay. So the statement is true for n equal to k plus 1 as well. So therefore by the principle of mathematical induction, we have Rn subset of R for all n belongs to natural numbers. Okay, so we are done here. Fine. Now one more thing here. So if we suppose we have a relation from a set A to B, and if we fix the ordering of the elements of A. For an example, if we say that the elements of A are A1, A2 up to AM, and the elements of B are some B1, B2, Bn. So if we fix the ordering, then we can make or we can compute a matrix from the set R or from the relation R. Okay, and that has also a special interest because
Sir,
yeah.
how you write this line? Then there exists x belongs to a such that a comma x belongs to r to the power k.
So that is the definition. So what is the definition of this? That what is the definition of your AC belongs to S compose R? So it means what is the definition of this? So that's mean there exists X,
Okay.
right? Such that AX belongs to R and XC belongs to S. Right? So that was the by the definition of the composition of relations. Fine. Okay, so good that you are asking that one. At least I feel that okay, there are someone who is listening to me. Otherwise, this online lectures are very boring. Okay. Now relation representing matrices. Okay. Now let R be a relation from a set A whose elements are A1, A2, AM to a set B which B1, B2, Bn. Okay. So here we choose a fixed ordering. Fixed ordering. Here also. Okay. So then the relation R can be expressed or can be represented by the matrix say MR whose entries are small mij, where mij equal to 1 if AI bj that in R and is 0 if AI bj not in R. That's mean if AI is related to bj, then we choose mij equal to 1, and if AI is not related to bj, this is j, then we take the entry mij as 0. Okay, this is simple. Now in this way we can define a matrix MR. Now you can see so there is a beautiful connection with this matrix with the relation R. So there are some observations. You can see that first observation. You can also prove these observations. So R is reflexive if and only if MII equal to 1 for all I. Right? So that's mean R is reflexive if and only if all the diagonal entries of the metric MR is 1. Okay, you can prove it because if it is not 0, then we will have some say j such that mjj is not equal to is 0. So therefore AI, right? So AI and bj, so they are not related. Okay, so first of all,
Why AI and BI gives a difference?
sorry. I have to take that one. So now for this I have to take, sorry. So now take A equal to B. So AI and AI. Okay. So then only we can see. Otherwise, if we know, so for talking about that reflexive, symmetric, transitive, we need a relation on a set, right? So therefore, we first have to take A equal to B, and then only we can talk about that reflexive, right? So this will be a right. So M cross M matrix in that case, say A1, A2 up to AM. Okay. Now if if MII 1 for all I, it is not true, then that's mean there exists a j such that mjj equal to 0. So that's mean aj is not related to aj. Okay, so therefore it will not be reflexive. So you can prove it. So this is just an observation which you can prove it. Now the second one is R is symmetric if and only if the matrix MR is symmetric. Okay. And the third one is this is one important observation which you need to work out a little bit. So R is antisymmetric if and only if either Mij equal to 0 or Mji equal to 0 for all I not equal to j. Right? Because suppose you have a I not equal to j such that Mij equal to 1 and Mgi equal to 1. So that's mean Ai and Aj are different, but you have Ai is related to Aj and Aj is related to Ai, but Ai is not related to Aj. Right? So that is a contradiction. So therefore this. So you should work out about this observation. You have to look into this. Okay. So just verify all of these observations. Right.
Sir, can you explain the third point once again?
Yeah, that's why I told you. So you should verify this by yourself.
Okay, sir.
Okay. So otherwise I am here, no problem. I will discuss it.
So if A is not equal to B, but they have equal number of elements, then the observation second and third will still hold.
No, because we generally take a relation on a set. Otherwise, there is no meaning of reflexive, right? Because the elements of A and B are different.
No, sir, only the observation second and third.
No, still we generally do not define that. We generally define symmetric relation on a set. That's mean right. So if you have if A and B are different, then we do not talk about the symmetric. That's mean we do not talk about the symmetric relation. MR can be symmetric, that matrix can be symmetric because the matrix has only 0 and 1, but we do not talk about the R is symmetric or not. Because R means A is related to B, right? And A, B should be in the same set. Otherwise, you cannot say that B is related to A. Because A cross B and B cross A, they are different in that case.
Okay.
Okay, fine.
Excuse me, sir.
Sir,
if we have a matrix of 3 by 3, like 1 0 0 1 1 0 1 1 1, then this is antisymmetric or not?
Which one? 1 0 0
1 1 0
1 1 0
1 1 1.
1 1 1. Yeah, that is antisymmetric.
But in third point, it's written that for all I not equal to j, Mij should be 0.
Why I have written that? I did not get your point. Yes.
Sir, in third point, it's written that R is antisymmetric if and only if either M. So in this case, Mij.
No, one of them is 0, no?
Okay.
One of them is 0. Means either here your means if you take any I and j where I not equal to j, you can see that that part is 0.
Yeah. Understood.
That is antisymmetric. Now, similarly, what we can ask that, suppose you have another example, say, and thank you for your example, because we got one example, right? And also you can check that this is not symmetric, right? And also it is reflexive. Now, if we take MR equal to say 1 1 0 1 1 1 and 0 1 1. Now, is it reflexive? Yes, right? Because all the diagonal entries are 1. Now it is symmetric. Yes.
Yes,
Again,
sir.
yes, because the matrix is symmetric, but it is not antisymmetric. As here M23 equal to M32 equal to 1, because both entries are 1, right? So that is not allowed, because we need at least, for I not equal to j, we need at least one of them is 0. Both can be 0, but we need at least one of them is 0. Okay, because
Sir, I cannot get the first one. I cannot relate it from the last definition of the antisymmetry, like A comma B belongs to R, B comma A belongs to R. Then
otherwise A2 is related to A3 and A3 is related to A2, and that will imply actually by the transitive, right?
so like
No, sorry. If it is antisymmetric, then sorry. If A2 is related to A3 and A3 is related to A2, then A2 should be equal to A3, right? That is
yes,
the
sir.
definition. But we know that A2 and A3 are different, so that is a contradiction. So that is very simple observation. You should see.
So it is a contradiction. Then how do we come to a conclusion that one of them should be 0?
Yeah, because if one of them is 0, if both of them, see, this is the if and only condition. If it is antisymmetric, so you just look at that. You just look at the proof. It is if and only criteria. So therefore, you can conclude that. So you can prove other way as well. So not this equal to not this, and not this equal to not this. So since this is if and only if, you can easily conclude that. So that was the reason I told you. So you should go through these observations. You should try to prove this. So these are very simple observations, not a difficult one. But if you want to write in terms of logic, then you have to give some arguments. So that's all. Okay. So now there is another thing that, so we know that composition of relations. Now we can easily find the matrix for the composition. Composition of relations. Now suppose MR, that is Rij, and say MS equal to say Sij, and say M, that matrix for S compose R, that is Tij. Okay. Then how to find this matrix? Now then Tij equal to 1 if and only if there exists K such that Rik equal to Skj equal to 1. Why? Because Aicj that is belongs to S composed R, that is by the definition if and only if there is a decay such that AI Bk belongs to R and Bk Cj belongs to S. Okay. So here we can assume that A, B, C, this is actually, so this is my R, this is my S, or you can take also all are same. Okay. So this part is clear, right? Oh, that should be R. Now this is actually equivalent to the Boolean product of matrix. Now this means matrix of S composed R is same as MR Boolean product with MS. So that is Boolean. So what is Boolean product? So in that case, Tij will be your this one, that is RI1 and S1j, then or RI2 and S2j, or RIN and SNj. Okay, and here that definition of 0, 1 is in that way. So that is also, it is known, right? It is in terms of true and false. So 0 and 0, that is 0, 0 and 1, that is also 0, 1 and 0, that is also 0, and 1 and 1 is 1. And if you take or 0 or 0 equal to 0, 0 or 1 equal to 1, 1 or 0 equal to 1, 1 or 1 equal to 1. Okay, so this is just a combination of 0 and 1, and in this way you can define a Boolean product, and you can check that that matrix is actually this. Okay, so therefore now see, now if you have a matrix, if you are given a matrix, then you can easily compute that M R square. That's mean you can now easily compute M R square from MR. So you can compute that. So that's mean if MR is given, then you can easily compute MR square. And then you can talk about that those are symmetric, anti-symmetric, or transitive. Okay. Fine. Now there is, okay, so I have around 10 minutes, so I can talk about this one a little bit. Now we have a relation. Now there is another concept called partial order relation. Now what is a partial order relation? So let X be a non-empty set okay. Now a relation R on X is said to be partial order relation if R is reflexive, antisymmetric, and transitive. So that's when it is similar types of, in the same spirit we have defined the equivalence relation, right? So similarly we can define partial order relation. For the equivalence relation we had reflexive, symmetric, and transitive. So here we have, for the partial order relation we have reflexive, antisymmetric, and transitive. Okay. Now the pair that X with the pair R, this pair is called a poset. Poset is a short form actually. So we generally call it as partial order set, or you can say the partial order relation on a set. So the set with the partial order relation is called a poset. Okay. And generally we do not write in this way. We generally write in this way, that X and this symbol. So this is the symbol this symbol is generally used for a partial order relation. Okay. Now this is a symbol. So you do not think this symbol as in general less than or equal to. Okay. So we call it is as a less than equal to because we have now a order, or say partial order, and there we have less than or equal to. That is fine, but it is not the usual less than equal to. Okay. So we should write that not the usual less than or equal. Okay. So we generally denote this relation by this symbol. Now we can see few examples. So we can take X equal to R. Okay. And that's when we can take X equal to real number, and we can take R is less than or equal. So that's mean usual less than equal to this one. We can take this R. Then we can easily prove that R is a partial order relation. Okay. Now this is one example. You can verify that. Now second one is, say X equal to say natural number, and say we define A related to B if and only if A divides B. Now similarly you can see that this is a partial order relation. So it is symmetric, anti-symmetric, sorry, it is reflexive, anti-symmetric, and transitive. Why it is anti-symmetric? Because if A divides B and B divides A, then the only possible option is A equal to B. Right? Now third one is, so if you take X equal to say power set of some set S, okay, and R is say this one. Now again this is reflexive because we know that A is a subset of itself, right? It is transitive because A is subset of B, B subset of C means A is subset of C. And why it is antisymmetric? Because A subset of B and B subset of A implies A equal to B. Right? So this way we can give many examples. So dual poset. Now what is a dual of a poset? Now let X less than or equal to R, be a poset. Okay. Now then the relation this one, that is the, if you say it is less than or equal to, this is greater or equal to, right? Now on X defining by, so defined by, we say that A that bigger or equal to B if and only if B less than or equal to A. So you feel it is trivial, right? But it is not actually trivial. So you can now prove that. So this is an exercise. Now prove that by defining this, this is a poset. Sorry, partial order relation. Partial order relation. That is very trivial to prove, but you need a proof to say that. Okay. Now the poset that X with that new relation is called the dual poset of this X that less than equal to. Okay. And finally, we can define covering relation.
Sir, not please can you explain the double poset? I'm not getting anything.
Sorry?
Can you please explain this double poset?
Huh?
I cannot get anything out of it.
I did not get your question actually.
I cannot get anything out of this double poset. What is this?
But you did not get what is this?
Yes, sir.
Oh, see, what is a order relation? Oh, sorry, we do not say that. Okay. Now, what is a? So you know, this is a partial order relation. On
Here this greater than equal to, what is this? Greater than equal to.
No, this is just a symbol. Now, first of all, this is a partial order relation on X. Okay.
Yes, sir.
And now you can define a new relation. For an example, so for a timing, you can forget about this. Maybe you are confusing with this one. So say this is R. Okay. Now let that X comma R be a poset. Now then you define another relation, say R dash. In this way, defined by A R dash B if and only B R A. Then you can prove that R dash is a partial order relation. It is easy to prove, right? Now this, the poset X comma R dash is called the dual poset of XR. Now is it clear?
X comma R dash. Sir.
Now it is clear to you?
Yes, sir.
Okay. Now here what we are doing, we are just using notation R by this and R dash by this. So that's all. For an example, if you look at this here, in this example, we will say that A this less than or equal to B if and only if A divides B. So that's all. So that's mean If you take 2, you cannot say that 2 is less than or equal to 3 because 2 does not divide 3. But 2 less than or equal to 4. So in this way, we can define you can say that new partial order. Okay. So this is why we called, I told you here, right? So I am writing here XR, instead of XR, I will use that less than or equal to. This symbol. This is just a symbol. It is not the usual less than or equal.
Sir, that symbol is
Sir, can you
making me
give an
confused.
example of dual poset?
Sorry. Okay, do you want an example of dual poset?
Yes, sir.
It is very simple. You can, in the case of third case, you can take this one and you can define your R dash is this symbol superset. Then you will get a dual poset. So if you take any power set of a set and if you take that subset of this one, if your relation, then that is a poset. And if you take another relation that is superset, then that will be your dual poset. Okay. So for X equal to say power set of S, dual poset of that X less than equal to is X, this one. It is not less than equal to, it is subset symbol and it is superset symbol. Okay, this is very simple actually. Okay, so I will start from this one. So I will repeat this part again in the next lecture. But that part is not very simple. That part is little bit tricky. So that is the reason I should send one email to all of you, because that number of students now it is 83. That should not happen. Okay, fine. So maybe I can stop now because it is already time is over.